mean?
The intersection.
The intersection. The intersection is the and region, right?
Yeah. The union's the what region?
The union is everything together. Okay. So the word and, which is associated with the symbol intersection, right, or I'm just going to read that as A and B because, you know, but it's technically it's A intersect B. So compound events, the word and, P, A, and B, they come in two forms, right? They are either independent events So, independent events are either two totally separate things, right? Either two totally different things. Like roll a die, toss a coin. Okay? If you roll a die, what effect could that have on the coin? None. Right? So then those events are independent. Right? If I roll a die and then I toss a coin, neither one of those can affect the other one. Right? So, two totally separate things. Or draw a card, toss a coin. Draw a card, you toss a coin. Does it matter if you draw the card first and then toss the coin, or toss the coin first and then draw the card? Doesn't matter, right? Because they're independent events. So if you are doing two totally separate things, those are independent events. If you're doing the same thing,
Dependent.
so for example, you're drawing a card and then drawing another card. So if you're doing the same thing, you will see the words. You're not going to hear them, some of you, because you're sitting chatting, but you will see the words. Okay, hey, please note, this is like vitally important. Okay, this is not like, just ignore this stuff. It's fine if you want to, but ignore it quietly, okay? Because I want the people who need to know this, because when you get hit by this next year, when you're heavy into the probability, it would be a really good idea if you had some idea what independent events were. Okay? So, it's either two totally different things. Those are independent, right? Toss a coin, roll a die. Roll a die, draw a card. If you're doing the same thing, you will see the words. You can anticipate them, but I don't think you're going to guess them. You will see the words
XOR.
with
what?
replacement.
What?
So you put the thing back.
In other words, I draw a card, I look at it, I then put the card back in. So the first event, I'm drawing from a full deck of cards. The second event, I'm drawing from a full deck of cards. Those will be independent events, right? Because you're starting with the same. Or I draw a marble from a bag of marbles, I take note of the color, I put the marble back in. Okay, so you'll see the words with replacement so that the second event has the same initial conditions as the first event. What would happen if I didn't put the card back? I'd have one fewer card, right? I would now be drawing from a deck of how many?
51.
51. Okay? If I had 12 marbles in a bag, I drew a marble out, didn't put it back. When I drew the next marble, how many in the bag?
I don't know how many marbles you started with.
-1.
Yeah, he just said 12.
No, I'm stupid.
No arguments. Okay, so if we draw from but if I draw from a bag of 12 marbles and then put it back, when I go to do the second draw, how many marbles? 12. So we got the same initial conditions, right? So if we're doing two totally separate things, by definition they're independent because they are different things, right? Which is the definition of independent. But if we're doing the same thing, drawing a card, then we have to, you'll see the words, if you don't see with replacement, it'll say it's put back or something along those lines, right? In other words, you got to be back at the same initial conditions for the events to be independent. Okay? So, independent events, the probability of independent events. P, A, and B.
Say what and what else each section is not.
Yeah, I'm going to. I just want to show you this.
What?
So the word associated with independent events is and. You're never going to see the symbol. And, or the word and, you are going to see A intersect B. So that's the formula that you're going to get. It's actually the formula that they've gone to now with Alberta Ed. Although you don't do probability in 30-1, so you don't have to worry about it. 30-2s do probability and they use those symbols. And we used to do probabilities in like applied 30 and pure 30 and they use the word and. So they've gone away from the wording and back to the symbols, which is how everybody else in the world does it anyways. Though I still like the words better. But yeah. So you just read them as the word and, right? So you see that, just say P, A, and B is probability of A times probability of B. Okay, so a coin is tossed, and a die is rolled. What's the probability of heads and 4? So the first thing you're asked of is, are those independent events? Yes, they are. So the probability of heads times the probability of 4. What's the probability of heads? What's the probability of getting a 4? Okay, and when I say die, default to 6-sided die. If I wanted it to be a 20-sided die, okay, so the probability of getting heads and 4 is 1/12, right? Makes sense. You could draw a tree diagram, show the outcome. How many outcomes are there when I toss a coin and roll a die?
2 times 12.
Yeah, 12, right? Head 1, head 2, head 3, head 4, head 5, head 6, tail 1, tail 2, tail 3, tail 4. You could list them, right? You could do the sample space. Not really all that difficult, right? H1, H2, H3, H4, H5, H6, T1, T2, T3, T4, T5, T6, right? And then if I wanted head and 4, you could just look in the sample space and say, okay, there's only one of them out of the 12. Okay, what is the probability of, let's do one more with this. Probability of tail and even. Are those independent events? Okay. Now, yes, because that's all we've done so far, you know, but in a moment we're going to do dependent events, and then when you're doing questions on this, the question you have to ask yourself is, are these dependent or independent events, right? So probability of tail times the probability of even. 1/2 times 3/6, which is 3/12, 1/4. I like the 3/12 because you could go into the sample space and count them 1, 2, 3 out of 12. That's what I call the raw probability, right? 3 out of 12. Okay, and then we reduce, right? 1/4. Raw probabilities are nice because everything to do with this experiment will always have a denominator of 12 because there's 12 possible outcomes. So if you want to compare them, you're not sitting there having to compare 1/3 with, you know, 1/4 or something like that, which is actually not all that hard, but you know, it's kind of doable. Okay, what if they are the same? What's the probability of now in this experiment, K1 is drawing a king as the first card, and K2 would be drawing a king as the second card. Okay, and we are doing with replace. So actually, wait, I should say what these are. Okay, so we're going to draw 2 cards. Draw a card. Replace it.
That would say draw a board.
Draw another card. Okay, probability K1 and K2 is, are these independent events? How do you know? Because you replaced it, right? Okay, so then the probability is K1 times the probability of K2. What's the probability of getting a king?
1 out of 52.
How many kings are there in the deck?
4.
How many cards in the deck?
52.
Okay, put the king back. Probability, how many cards, kings are in the deck?
1.52.
Okay. And I'm okay with the reduced fraction formula, so it's 1 over 169. Okay. If you do need to compare probabilities, then you're just going to convert them to decimals. Right, unless they all have a 169. Because it's a standard deck of cards. And with a standard deck of cards, we don't include
I played
jokers.
poker.
Oh, which page? Oh, which page? No, I don't play poker.
We're now moving to page 483.
Asian games, OP.
Dependent events. This is where the outcome of the first event affects the outcome of the second event. Okay? So the outcome of the first event. Okay, first of all, it's associated with the word and. Also, right? It's still an and probability. We're not doing or probabilities till next week. So dependent events are associated with the word and. You're doing the same thing. Okay? Because if you're doing different things, then what kind of events are those? Those are independent, right? Because they're different things, so they would be independent. Dependent events, you need to be doing the same thing. And what words will you see?
Without replacement.
Without replacement, we're not going to put it back. So it's got to be the same thing, because if it's different things, then they're independent events. If it's the same thing and you see the words with replacement, it's independent. Because that means you're just going back to the original starting conditions. If you see the words without replacement, then it's dependent. Right? So that the outcome of the second event depends on what happened the first time, right? Because now I have one fewer king in the deck. But I also have one fewer card in the deck. So if I want to draw two cards without replacement, well, let's do it. Actually, first we need the formula.
P union. A union.
Or the one that you're going to see.
I already don't like it.
What isn't it union?
Yeah, it is. Oh, no, it's not union. It's
what?
It's intersection.
Yeah, union is.
Union is or. Union is bringing together.
It's a valley where everybody falls in and heck it out. That's all we know.
It brings it all together.
No, it doesn't.
It's a higher probability than any individual probability. An and probability is less likely than the individual thing because more than one thing, they both have to happen, right? So with an and probability, you multiply because you want to get a smaller fraction, right? Remember, you multiply two fractions, you're going to get a smaller one, smaller number. With an or probability, which we haven't got to, the union, you're bringing things together because it's more like, well, you belong to this group or this group, we're bringing you together. You're going to have a larger probability than either of the individual ones. Okay? We don't do them. This means, given, well, actually, this means given. Just the line. The line is given. So it's read as the probability of A intersect B, or A and B, is the probability of A times the probability of B given that A has happened. Okay? So given that A has happened, what's the probability of B happening? So let's try this then. We'll draw two cards. So two cards are drawn. Drawn without replacement. It has to be specified, right? You know, or a card is drawn and then another card is drawn. Okay, that would imply without replacement. Okay, so it may not be specifically stated, but it would be implied by reading the card. Okay, card is drawn, then a second card is drawn. Okay, did you put the first card back? It doesn't say, so I don't think so. Right, because they would have explicitly said. What's the probability of K1 and K2? So, formula, it's probability of K1 times the probability of getting a king on the second draw given that you got a king on the first draw. Okay, what's the probability of getting a king on the first draw? 4 out of 52. We didn't put it back. How many kings are left in the deck? 3. And how many cards are left? Okay, what's that reduced to? I think it's 1 out of 221, but you might want to check that. I'm just doing that from memory. But I think it's 13 times 17. Yeah, good. I remembered. Okay, so we have to be doing the same thing, right? Draw, because otherwise they're independent events. Okay, let's try another one. A bag. Contains
Why so much English?
2 red, 3 blue,
Contains.
5 yellow, and 6 orange marbles.
Oh yeah.
They're all colors of the rainbow, so they're good. Roy G. Biv. I have another way of remembering it, but it's not suitable. Mixed company. No. It's actually for remembering resistor colors, because resistance is used the same colors, but they also have black, brown, and white. So you have to.
No.
Yeah, well, there's that too. But okay, so. Okay, what's the probability of drawing a red marble, then a blue marble if the first marble is replaced? What kind of events? Independent. What formula?
The first one.
Red intersects blue. So probability of red times probability of blue. What's the probability of red? How many reds are there? How many marbles are there?
2 out of 10, so 1 out of 16.
Learn to count. Okay, how many blue marbles are there?
3.
How many marbles are there?
16, 3 out of 16.
Okay.
So 6 out of 256.
Can you please simplify that?
Okay.
Oh, do we have to use that in actuarial science?
You'll never know.
That'd be the question. Probably.
Okay, what's formula?
King R times
Okay, so if I want to get a red and then a blue, and I am not replacing the marble, which makes them what kind of events? Makes it a dependent event. What's probability of red? It's always the same, right? Doesn't matter, because nothing changed from here to here. But now things change. How many blues are there?
3 out of 15.
Okay, so we had 3 out of 15. 6 out of, I don't know, 240 maybe? 1 out of 40? Okay, I don't know, you should check, but otherwise that's... Okay. So, independent events, we put it back, it's the same set of starting conditions. Your denominator will be the same for the second event as it was for the first event, because you're starting with a full deck or you have a full bag of marbles, or you're playing with all your marbles, which some of you don't. Nor do some of you play with a full deck. But you're playing with a full deck or a full bag of marbles. for dependent events, you've drawn out. So if I wanted king and a queen as dependent, it would be 4 out of 52, then 4 out of 51. Right? Because the denominator would go down. So for dependent events, your denominator is always going to drop by 1. Because you've done something, but you haven't put it back. For independent events, your denominators are going to stay the same. Okay? Your numerator, it depends what the event. If this was red and red, this would be 2 out of 16, 2 out of 16. This would be 2 out of 16, 1 out of 15. Right? There's only one red left. Given that I've got, because this has happened, right? Given that I've done this, how many, whatever, if that was a red, given red, then there would be 1 red left out of 15.
Which page are you on?
It says keep going. That does tree diagrams.
A sampling within the.
Sampling without replacement. Okay, well, without replacement we've already done, right? Yeah. Sampling simulation. No, we don't do Pascal strength. Yeah, no, we only go to 489. So using tree diagrams. Sampling. All right. Well, okay. Maybe we do one with a tree diagram and.
Or do we have to use Venn diagrams to do it?
That's Monday. Okay. Tree diagram and probability.
Oh no. There's more.
Mary. Either sets her alarm clock or forgets to. Black sheep.
But in theory, his heart can still be functioning.
Don't say. Doesn't the alarm clock go automatically down? You just set it and then you just leave it there.
Sorry, no money for that. Ain't nobody going to do that. I'm sorry.
I just leave it there.
Okay.
Be late.
So Mary either sets her alarm clock. If she doesn't, if she sets her clock, which is 62% of the time, the probability that she will be late is 0.2.
Doing this question just for more seat.
Teach Mary to move him.
Okay, 0.7 if she doesn't set it.
That's one question.
That's like 3 that we call.
Okay. So here's the full scenario. Mary either sets her alarm clock or she doesn't. 62% of the time she does. If she does set it, she's got a 0.2 probability of being late. If she doesn't set it, probability she's late 0.7. Today she was late. What is the probability that she set her clock? So the way that we're going to solve this, we're going to do a tree diagram. Okay? a tree diagram. So we're going to say that either she sets her clock or she doesn't set her clock. What's the probability she sets her clock?
62%.
Okay, we're going to call that 0.62. What's the probability she does not set her clock? 0.38. Why?
Because they're dependent events.
These are called complementary events. Let's throw out words you just learned without knowing what they mean. These are called complementary events, right? Because you either do it or you don't. There's only two possibilities, set or don't set. After she sets, then there's probability late, not late, late, not late. If she sets it, what's the probability that she's late? 0.2. What's the probability she is not late? 0.8. If she doesn't set it, what's the probability she's late?
0.7.
What's the probability she is not late?
0.3.
Okay, so we end up with set and late. Set and not late. Not set and late. Not set, not late. What's this probability? 0.62 times 0.2, which is 0.132, right? I think. I don't know. What's this one? 0.8, which is?
It's 0.124.
That's 0.124?
Yeah,
Okay.
I think. Check them out.
No, I think you're right.
It is.
67, I multiplied 67. What's 0.62 times 0.8?
496.
0.496. Okay, what's this probability? 0.38 times 0.7. What's that work out to? 6.
0.266.
Okay. And what's this probability?
Next one. Actually, it's half anyway.
0.38 times. Add 0.11.
What do these add up to?
1.
You sure?
Oh, you should.
Well, yeah, we know what they should add up to. What do they add up to?
0.999.
That actually might happen. No, because that is 1.
1.
But
Exactly.
Just 1.
it's 1.
4.9.
It's 1 because these were accurate to 3 decimals, right? If we were doing stuff where you were rounding at 2 or 3 decimals, then you might not add up to 1. You could go slightly over, you could go slightly, might be 0.999, 0.998, 1.01, whatever, right? But you still know that it was 1 that you had just, you're using a rounded value. Okay, so the question was, given that she's late, what's the probability she set her alarm clock?
124 plus 0.266.
So give it, so where is she late? Let's deal with, so which ones were late? This one?
Yeah.
And the other one.
And the other, this one? No.
No.
Okay. So, we know she's late. What's the probability that she, what did we say, did set her alarm clock? But yeah, what's the probability that she did set her alarm clock?
So like 124 over 0.266.
What is it total?
Out of
Yeah, it's total.
Probability, what did we say? It was set?
So we're doing for the 3, 1, 3.
0.124 over
0.124.
okay, which is
0.3118 basically. I rounded
You wrote not late.
can't fix it without. Okay, 31.8%, right? So what we were doing there was we said, hey, wait, we know that she was late, which means that we're dealing with these two probabilities that have her as being late. And the probability that she set her alarm clock is favorable, 0.124, that's that she set her alarm clock. But not out of 1, right? It's out of the probability that she was late, which is the sum of those two. Okay? That's what I never showed the 30-2s because they wouldn't. No.
Extra does.
Yeah. They won't be tested on that either, right? So, okay. Anyways, that's using a tree diagram, right, where we have different probabilities in the tree. We did one with the probability before. It was like boys and girls. It was the halves all the way around, right? But these are the different probabilities, right? She sets it and she's late. She sets it and she's not late. She doesn't set it and she's late. She doesn't set it and she isn't late. That's every possibility, right? There are only 4 possibilities, so we deal with all of those. And they have to add up to 1. But then we're interested in a subset of those when we go to calculate the actual numbers.